Hello, STT 315. This is recitation 8. So let's start with question 1. A roll of plastic-coated wire has an average of 0.8 flaw per 4-meter length of wire. Suppose a quality control engineer will sample a 4-meter length of wire from a roll of wire 220 meters in length. If no flaws are found in the sample, the engineer will accept the entire roll of wire. What is the probability that the roll will be rejected? What assumption did you make to find this probability? So this is a Poisson random variable because we are counting number g times a certain event occurs within a given unit length. So here, since we're in a Poisson random variable setup, we're given that our average is 0.8 flaw per 4-meter length of wire. So lambda denotes our average in a Poisson random variable. So I wrote that information here. And so we're interested in the probability that the roll will be rejected. So that means that the probability that x does not equal 0, because if no flaws are found in the sample, the engineer will accept the entire roll. So we're interested in the probability that, the probability that x does not equal 0. So we have 1 minus the that equals 1 minus the probability that x equals 0. And since we're in a Poisson setup, we can use R and use the PPOIS function. And here x is 0, and our lambda we said was 0.8. And so R will give you that PPOIS 0, 0.8 is 0.449329. So 1 minus that is 0.550671. Okay, so moving on to question 2. Assume that x is a binomial random variable with n equal to 1,000 and p equal to 0.5. Use a normal approximation to find each of the following probabilities. So first, we're interested in the probability that x is greater than 500. So I normally like to draw a picture here. So if here we have a binomial random variable, here's our distribution. So our we're interested in, well, first let's find the mean and standard deviation, and then we can fill out what the mean is. Spoiler alert, it's 500. So, and for a binomial random variable, the mean is n times p. So here our n is 1,000 and our p is 0.5. So when you multiply those together, you get 500. And our standard deviation is the square root of n times p times q, which q is the probability of failure. So you can compute that by 1 minus p, that equals q. So here we have 1,000 as our n, p as our 0.5, and then q is our 1 minus p, so 1 minus 0.5, which is 0.5. So when you multiply those together and you get 250. So then you take the square root of that and you get 15.8114. So that's the standard deviation. So here then you can draw your density, and I know, okay, 500, we're interested in the probability that x is greater than 500. So here it just so happens the mean is 500 as well. So we're interested in the area under the curve from 500 onward, like towards infinity. So when you put that into your calculator, oh, this should be binomial, not normal. Sorry, that was my fault. Okay. Oh, no, sorry. No, it is normal because we're doing normal approximation. Okay, my bad. So, yeah, that's what I said before. So the probability that x is greater than 500, we're going to do normal CDF in our calculator. So our lower bound in this situation is 500. Our upper bound is infinity, so we're going to do 10 to the 10. And then our mu is 500, that's our mean, and our standard deviation is 15.8114, that's a 4. So then we get, when you put that in your calculator, you get 0.5. And that is what I would expect because 500 is our mean. So if we take the area under the curve from that point onward, it should be exactly half the area under that curve. So, and this is the normal density. I'm not sure if I said binomial earlier, but it's the normal density because we're doing normal approximation. Okay, on to the next one. We're still in the same setup, so don't forget our mean is 500 and our standard deviation is 15.8114. So now we're interested in the probability that x lies within 490 and 500. So I always draw a picture first. So here we have our normal curve. Sorry about that. I'm going to mute myself for a second. Okay. Sorry about that. All right. So here we have our mean is 0.5. Our mean is 500. So I'm going to mark that down. And now I'm going to write our like two bounds that were given in the problem. So we have 490 on one side and then 500 on the other. So we're interested in the area under the curve in between these 2 points. So we're going to do the normal CDF function again. In our lower bound, this time is 490. Our upper bound is 500. Our mean is 500 and our standard deviation is 15.8114. So when you put that in your calculator, you should get 0.2365. So that's the area under the curve. Now, part C is the probability that x is greater than 550. So I'm going to draw the same type of graph. So here we have our mean is still 500. And then we have 550 would lie somewhere to the right of the mean. So somewhere over here. And we're interested in the area under the curve starting from that point towards infinity. So we're interested in the area here. So our lower bound is 550. Our upper bound is infinity. So we're going to input in our calculator 10 to the 10. And then we have 500 as our mean and 15.8114 as our standard deviation. And your calculator should give you 0.000783. So that's that area, the shaded region. Okay. Question 3. Personnel tests are designed to test a job applicant's cognitive and or physical abilities. The Wonderlic IQ test is an example of the former. The Purdue pegboard speed test involving arrangement of pegs on a pegboard is an example of the latter. A particular dexterity test is administered nationwide by a private testing service. It is known that for all tests administered last year, the distribution of scores was approximately normal, with mean 75 and standard deviation 7.5. Part A, a particular employer requires job candidates to score at least 80 on the dexterity test. Approximately what percentage of the scores during the past year exceeded 80? So here we're interested in the probability that the candidate scores at least 80 on that dexterity test. So that's the probability that x is greater than or equal to 80. So we're going to use the normal CDF function. And I like drawing, my density. So we're given that the mean is 75 and our standard deviation is 7.5. And so here we're interested in the probability that x is greater than or equal to 80. So I'm going to put my 80 somewhere over here because it's larger than 75. and I'm interested in the area under the curve from 80 towards infinity. So my lower bound is 80, my upper bound is infinity, so I'm going to put 10 to the 10, and then my mean is 75, and our standard deviation is 7.5. So you put that in your calculator and you should get 0.2525. So that's that area under the curve. So that's the percentage of the test scores during the past year that exceeded 80. Okay. The testing service reported to a particular employer that one of its job candidates' scores fell at the 98th percentile of the distribution. So approximately 98% of the test scores were lower than the candidates and only 2% were higher. That's what 98th percentile means. So what was the candidate's score? So here we're going to be using inverse norm because we're interested in the exact score. We know we're given the area under the curve. We're given that here on the left-hand side, 98% of the scores are lower than candidate X0, the candidate score of X0, and then 0.02 is higher than that. So when we put it into our calculator, though, we're going to use 0.98 because our calculator goes from left to right, goes from negative infinity towards positive infinity. So the area under the curve we're going to use in our inverse norm function is 0.98 opposed to 0.02. And then our mean is 75 still, and our standard deviation is 7.5. So you put that in your calculator and it'll give you 90.4. So that is X, that equals X0. That is the candidate score. Okay. Question 4. Timber beams are widely used in home construction. When the load measured in pounds per unit length has a constant value over part of a beam, the load is said to be uniformly distributed over that part of the beam. Consider a cantilever beam with a uniformly distributed load between 100 and 115 pounds per linear foot. So we're in a uniform distribution situation. Part A, what is the probability that a beam load exceeds 110 pounds per linear foot? Okay, so here we're in uniform distribution. Our C is 100 and our D is 115. So if we were to draw that out, it's going to be 0 everywhere except in the range of 100 to 115. Well, I shouldn't say range, where X is 100 to 115. And this height here is 1 over D minus C. And so our D is 115, our C is 100. So 115 minus 100 is 15. So the height of this is 1 over 15. So I start off by drawing what the density looks like of the uniform distribution. And now, going back to the problem, what is the probability that a beam load exceeds 110 pounds per linear foot? So here, 110 is somewhere in here, and I'm interested in the area under this curve, even though it's not really a curve. The area under here from 110 onward. And so the probability that X is greater than 10 is 115 minus 110 divided by 115 minus 100. And how do we get this? So here, the formula you should have been taught was B minus A divided by D minus C. So our D and C are here, given for the distribution, and our B is the upper bound of the interval we're interested in, and our A is the lower bound of the interval we're interested in. So in this situation, we're interested in the interval of like 110 to infinity, but we know that once you get past 115, it's going to be 0. So we're interested in the interval of 110 to 115 to find the area under there. So our upper bound, our B in this situation, would be 115, and our lower bound is going to be 110. So that's why we get 115 minus 110 in the numerator. And then the denominator is D minus C. So our D is 115 and our C is 100. So when you plug and chug, you get 5 divided by 15, which is 0.33 repeating. So that is the probability that a beam load exceeds 110 pounds per linear foot. So here the shaded area is 0.33. What is the probability that a beam load is less than 102 pounds per linear foot? So here I always start off with, drawing what we have. So here it's going to be the same. We're in the same density of, we're in the same, situation of uniform. So we have, it's from 100 to 115. The height is 1/15. And so now we're interested that in the probability that the beam load is less than 102. So we're interested in the shaded area from 100 to 102. So here, our upper bound in this interval is 102. Our lower bound is 100. So that's the numerator divided by 115 minus 100. So when you simplify, you get 2/15, which is 0.133. Find a value L such that the probability that the beam load exceeds L is only 0.1. So here, this is kind of similar to like our inverse norm function, even though we're not in a normal setup, where we're given the area under our curve, even though it's not a curve. And then we want to find that specific value. So this is probability of x greater than L equals 0.1. So here we can do, we know that our upper bound in our interval we're interested is 115. And then our lower bound, we don't know. That's what we're trying to find. So that's L. And then our denominator stays the same, 115 minus 100. So then you just solve this algebraically. So you get 115 minus L over 15 equals 0.1. So then you can multiply by 15 on both sides. So then you get 115 minus L equals 15 times 0.1. And then you can subtract 1.5 on both sides and add L on both sides to get 113.5 equals L. So that is what our question mark is on the x-axis, is 113.5. Question 5. Consider x normally distributed with mean 55 and variance 1.2. Let y be normally distributed with mean 72 and variance 5. Also, let x be independent of y. Then find the probability that w is less than or equal to 200, where w equals x plus y. So here, I'm going to write this same information that we were given up here. So we have our x is normally distributed with our mean 55 and so we were given variance. So our standard deviation is the square root of 1.2. And then our y is normally distributed with our mean 72 and standard deviation of square root of 5, because we were also given variance again. So you take the square root of the variance to get the standard deviation. So we get the square root of 5 for the standard deviation of y. And then we're given that x is independent of y. and that W equals X plus Y, and that we want to find the probability where W is less than 200. All right, so I'm going to scroll down since I wrote down all of our important information on the left. So here, our W equals, a normal distribution with a mean mu, which we'll need to find, and a standard deviation. So first, we need to find those because in the end, we're going to use that to input our normal CDF. So first, let's find the expectation of W, our mean. So we have our W is X plus Y. So the expectation of W equals the expectation of X plus Y. And then because we're given that they're independent, the expectation of X plus Y equals the expectation of X plus the expectation of Y. So that's because of independence. And then we're given the expectation of X alone and the expectation of Y alone. So that's 55 plus 72. And you can look right here if you don't remember what I'm talking about. So you add those together, you get 127. So 127 is going to equal mu of W. Now we want to find the variance of W to eventually find the standard deviation of W. So the variance of W equals the variance of X plus Y. And because of independence, that equals the variance of X plus the variance of Y. And then we're given what the variance of X alone is and what the variance of Y alone is right here. So we have, this should be the square root. So sorry, I think I calculated this wrong. So the variance of, oh wait, no, I didn't calculate it wrong. So I'm just calculating the variance right now. So yeah, the variance is 1.2 of X, and then the variance of Y is 5, because that's given here. And then you add those together, that's 6.2. And then we want to take the square root of that to get the standard deviation. So I did it right. So the square root of that is, so the standard deviation is the square root of 6.2. So if I were to fill in the information we just found out, we have that W follows normal with the 127 mean and square root of 6.2 standard deviation. And then our end goal is the probability that W is less than or equal to 200. So if I were to draw our normal density, we have, we're interested in, so here's our mean, which is 127, and we're interested in the area under the curve from -infinity up to 200, so this shaded region. So when we plug that into our calculator, we'll do normal CDF because we're interested in the area under the curve, and then we'll have from -infinity, so I'll do -10 to the 10, and then our upper bound is 200. Our mean is 127, and our standard deviation is the square root of 6.2. And so then when you put that in your calculator, mine rounded it up to 1. So yes, so that's what you should get when you put it into your calculator. So this picture isn't completely drawn to scale because 200 would be like even further out where, the area under the curve past 200 is like negligible, because my calculator gave me 1. But anyway, so moving on to the next part, something to keep in mind. So if X follows a normal distribution with mean 0 and standard deviation sigma, and Y equals A times X plus B, where A and B are real numbers, then Y is also normally distributed with the following. So the expectation of Y equals the expectation of ax plus b, because that's what we're given, y equals. And then when you want to take the expectation, here you can think of like distributing the expectation, well, not distributing the expectation, but the expectation wants to hang on to x, because you can take the expectation of x. So you just do a times the expectation of x and then plus b. So the expectation of a constant b is just that number. So we have a times the expectation of x plus b, and the expectation of x is mu. So this would equal a mu plus b. And then the variance of y is slightly different. So the variance of ax plus b, so when you kind of think of distributing the variance in a way, when you put the variance inside, you're going to get the variance of x, but when you take a constant outside that's multiplied by x, that becomes squared for the variance. And then if you just take a variance of a constant alone that's not multiplied by x, you're going to get 0, because a variance of a constant, the variance of a constant is 0. So you get a squared times the variance of x plus 0, and the variance of x in this situation is sigma squared. So you get a squared times sigma squared. And so then with both of, now that you found the expectation of y and the variance of y, that implies that y follows a normal distribution with the mean of a mu plus b, and then our standard deviation of a sigma, because remember, the standard deviation is the square root of the variance. So if you take the square root of a squared sigma squared, you get a times sigma. So that's something to keep in mind. And then now we're going to be going over the results of the homework that was due this week. So here we have the following table gives the results associated with a lie detector test given to a group of individuals. So here we have, so if we have, you can either test positive or test negative, and you can be lying or not lying. So we're given this data and we want to find what is the probability that a person chosen at random from this group is lying and the test detects it. So here we want the situation where, so if you test positive, that means the test detects you're lying. If positive means that the test thinks you're lying, negative means that the test thinks you're, telling the truth or not lying. So what is the probability that a person chosen at random from this group is lying and the test detects it? So that would be 28, because that would be that you're lying and that the test detects it, so the test is positive. And then divided by the total number of people. So I just put the totals for the rows and the columns here, and then I totaled up everything. So it's out of 100 total people. So 28 out of 100 is 0.28. Next, given that a person is lying, what is the probability that a test detects it? So here, given that a person is lying, so here the total for that row is 35. So we're only in that situation. What is the probability that the test detects it? So the probability equals 28, because this would be the test being positive means that the test detects someone's lying. So that would be 28 divided by 35, because it's given the person is lying. So when you do that, it's 0.8. Given that the test gives the conclusion the person is lying, what is the probability that the person is actually lying? So here we would have so we're given that the test gives the conclusion the person is lying. So 28 plus 16 sorry, I had a brain fart for a second. So given the test gives the conclusion a person is lying. So that means that the test is positive. So that would be in the denominator. So that would be 28 plus 16. So the total for the test positive column would be in the denominator. And then what is the probability the person is actually lying? So if the person is lying, it would be 28. So 28 divided by 44 equals 0.64. And then let A be the event the person is lying and B be the event that the test concludes the person is lying. Which of the following is correct? So that would be that A and B are neither mutually exclusive nor independent. Next, consider a test that has known reliability when administered to an ill person. The test will indicate so with probability 0.94. When administered to a person who is not ill, the test will erroneously give a positive result with probability 0.18. Suppose the illness is known to affect only 10% of the population. What is the probability that on a randomly picked person, the test shows positive? So here we want to know the probability that the test is positive. And so we have, we would do 0.1 times 0.94 plus 0.9 times 0.18. So let me kind of show you, let me see if I can zoom out a little bit so you can see all of this at once. So if I plug in what we know, so for a test result that's ill, positive, we have that here for an ill person, the probability that the test result will show that they're ill is 0.94. For a healthy person, a false positive probability of 0.18. And then we're also given that the illness is known to affect only 10% of the population. So here we would do 0.1 because that's 10% of the population times 0.94, and then plus the probability of 0.9, which is 1 minus 0.1, and then 0.18. So you get 0.256. And then if a person is randomly selected from the population and is given the test and the result is positive, what is the conditional probability that the person is actually ill? So we want to know the probability of having an ill person given that the test is positive. So you would do 0.1 times 0.94 divided by the probability that the test is positive, which we found earlier, which is 0.256. And then we get 0.367188. So we get the correct solution there. Next, when the economic situation is high, a certain economic indicator rises with probability 0.55. When the economic situation is medium, the economic indicator rises with probability 0.31. When the economic situation is low, the indicator rises with probability 0.14. The economy is high 18% of the time. It is medium 74% of the time and is low 8.0000000001% of the time. Fill the above table on your paper and answer the next 3 questions. Okay, so I is the event the indicator rises and D is the event that the indicator fails. So let's plug in the values in this table first. So here we were given this first row. So 0.55 is when the economic situation is high and the indicator rises. So that's here 0.55. Then 0.31 is when we are in the medium, the economic indicator the economic situation is medium and the indicator rises. So that's 0.31. And then here, we have 0.14 for where the indicator rises and the situation is low. So to get the bottom row, the D row, we're going to do 1 minus what we get in the first, like the space above, because if it doesn't rise, then it fails. So we're using the property of 1 minus, like A complement equals 1 minus the probability of A type rule. So 1 minus 0.55 is 0.45. 1 minus 0.31 is 0.69. 1 minus 0.14 is 0.86. And then I just wrote the other information here where the probability or the economy is high 18% of the time, is medium 74% of the time, and is low 0.08% of the time. So here's our information. And so let's see what the first question is asking. What is the probability that the economy is low and the indicator fails? So that would be, here we have our keyword is and so that's an intersection situation. So we have the probability of L intersect D. So L is low and D is fails. So in a previous recitation, we learned that the probability of the intersection equals the probability of L times the probability of D given L. So the probability of L is 0.08 and the probability of D given L, so the probability that it fails given we're in the low situation would be 0.86 here. So the lower right-hand corner of this chart. So when you multiply those together, you get 0.0688, and then it'll be 0.00001, because they didn't write all the zeros after this, and then the 1 for the probability of low. But you'll get this as your correct answer. What is the probability that the indicator will fail? So here, fail, remember, is D. Is the event that the indicator fails. So the probability of event D equals the probability, here we're using Bayes' rule, so the probability of H times the probability of D given H, and then the probability of M times the probability of D given M, and then the probability of L times the probability of D given L. So the probability of H is 0.18. The probability of D given H would be 0.45. The probability of M equals 0.74. The probability of D given M is 0.69. And the probability of L is 0.0800000001. And then the probability of D given L is 0.86. So when you multiply those three values and then add them together, you get 0.6604. Given that the indicator has fallen, what is the probability that the economy is high? So here, given is our keyword that we're going to be in a conditional probability situation. So given the indicator has fallen, so if it fails, that's event D. What is the probability the economy is high? So that's H. So the probability of H given D equals the probability of H times the probability of D given H divided by the probability of D. So we know all those three values. So here probability of H is 0.18. The probability of D given H is 0.45. And the probability of D is 0.6604. So you plug and chug, and that's 0.1227. The above table gives partial information on the distribution of a random variable x. It is known that the probability of x less than or equal to 3 is 0.5. Using the above table, find the probability that x equals 5. So here we were given that the probability that X is less than or equal to 3 is 0.5. So that means when you add up all of these three values, they should equal 0.5. So to find this missing value, because I had a missing value for 3, I'm going to do 0.5 minus 0.16 minus 0.19, and that'll give me 0.15. So I can plug in this missing value, and now we want to know the probability that X equals 5. So we're looking for what is this probability in this last square here. So we would do 1 minus all of these probabilities added together, because we know that them all added up should be 1. So when we do that and we subtract all of these values from 1, we get 0.37. So that would go in this last box here. What is the probability that X falls within 2 and 4? So we're going to add up these three values. We're going to add up the probability where X equals 2, the probability where X equals 3, and the probability where X equals 4. So when you add those three values together, you get 0.47. Okay. An appliance dealer sells 5 types of air conditioners. The above gives the distribution of the random variable X, tonnage of air conditioner bought by a customer. What is the expectation of X? So here we have on the left-hand side how many tons, and then on the right the probability. So associated with the amount of tons. So for the expectation of X, we would do 1 times 0.17, and then keep working our way down. So plus 2 times 0.26, plus 5 times 0.11, plus 10 times 0.11, plus 20 times 0.35, and that gives you 9.34. So that is the expectation of X. The standard deviation of X, so we're given, so that's the square root of the variance. And so we are given that the variance is the sum from I equal 1 to n of pi times xi minus mu squared. So we're going to plug in all of the values in this sum here. So we're going to do, don't forget the square root. And then we have, so when I equals 1, we have, so P1 is the first probability. So we have 0.17, and then multiply that by xi minus mu squared. So x1 is 1, and then minus 9.34, which is what we found the expectation of X here. That's mu. So minus 9.34 squared, and then we're going to add that to when our I equals 2. So when our I equals 2, our probability is 0.26, and then we have our xi is 2 tons, so 2 minus 9.34 squared, and then we're going to keep going down the row all the way to the last, which is 0.35 is our probability, times our X of 20 minus 9.34 squared. So when you put all that in your calculator, you should get the square root of 67.7244, which equals 8.22948. The air conditioners are priced by the retailer at $200 per ton. The retailer pays $100 per ton to buy the air conditioners. In addition, there is an overhead cost of $50 per air conditioner. What is the expected value of profit for the retailer from the sale of an air conditioner? So we're going to let Y equal profit. So Y equals 200x, because it's the air conditioners are priced at $200 per ton. So that's how much they're like charging their customers. And then minus the retailer pays $100 per ton. So that would be minus, sorry, did I say per air conditioner earlier? I meant per ton. So we have 200x and then minus 100x because that's how much the retailer has to pay. And then there's also overhead costs. So then we also are going to just subtract 50. So we need to go through and do this for every x that we have. But we're taking the expectations, so we also have to multiply it by the probability. So here we have 200 times 1 ton, minus 100 times 1 ton minus 50 times, and then in blue I put the probability, so times 0.17. And then we're going to add that to the next one we're going to get, which is 200 times, so now we have 2 tons and probability of 0.26. So here our x is 2 and our probability is 0.26. So then you're going to keep going down the column, and so then you'll get 49.5 when you're in 5-ton situation, and then when you have 10 tons, you'll get the 104.5, and then at last, when you have 20 tons, and then the probability of 0.35, when you plug that into here, you get 68.25. So you add up all of these values together, and then you get 884. So that is that's the expected value for the profit. So the expectation of Y. Now, what is the standard deviation of the profit from the sale of an air conditioner? So we want to find the standard deviation of Y. So here, if I were to simplify my Y equation, I have 200x minus 100x can simplify to 100x and then minus 50. So the standard deviation of Y is 100 times the standard deviation of X. And then that equals 100 times 8.2295. So you get 180 or 822.95 as your answer. X is a random variable with expectation of X equal 10 and variance of X equals 12.5. So now we want to find the expectation of negative 6x plus 12. So this is what we talked about. Where is it? Way up here. We're going to be using that. So now I gotta find it again. So the expectation of that is we're going to take the expectation. We're going to bring the expectation inside, so we get negative 6 times the expectation of X plus 12, because the expectation of a constant is just that constant itself. So you get negative 6 times 10, because we're given the expectation of X is 10 plus 12, so that's negative 48. So negative 60 plus 12 is negative 48. And then the variance, so find the standard deviation. But we're given the variance up above. So first we'll find the variance, and then we'll take the square root at the end to get the standard deviation, which is what we're ultimately looking for. So the variance of negative 6x plus 12 is, so when you put the variance inside, or you take the constant outside that's multiplied by x, you're going to square it. And then the variance of a constant is 0. So we get negative 6 squared times the variance of x. So then that equals a positive 36 times, and then we're given the variance of x is 12.25. So that's 36 times 12.25, which equals 441. But we're not done yet, because we need to find the standard deviation. So we'll take the square root of 441, and that equals 21. Okay, this is the last question. All voters of Milwaukee County were asked a week before each election day whether they would vote for a certain presidential candidate. Of these, 40% answered yes, 44 replied no, and the rest were undecided. So I wrote that down here. If A yes answer is coded, or is coded +1. A no answer is coded as -1, and an undecided answer is coded as 0. So I just put the codes in blue here. Find the mean and the variance of the code. So here the mean is 1 times the probability of, so here a yes is coded as 1. So here we have 1 times the probability of 1 occurring, which is 0.4. So 1 times 0.4, and then plus a -1 times 0.44. So that's -1 times 0.44, and then plus a 0 times 0.16. So that equals -0.04 as our mean. And then our variance is the same equation we used before. So we have our PI, or P1 is 0.4. That's the probability. So our probability is 40%. So 0.4 times, here our code is 1. So 1 minus, and then we found that our mean is 0.04. So we would get, I may have messed up my signs, did I? I may have put it in my calculator right, but then you would do xi minus mu, which our mu is -0.04, and then you would go on to the next one. So you would have 0.44, and then -1 minus 0.04 squared, and then 0.16 times 0 minus 0.04 squared. So then you get 0.8448. And I hope this was helpful. See you next time.